Hello and welcome to another edition of our short clip video series. My name is Ole Carstensen, and in the following video I will demonstrate how to calculate the discharge voltage profile of a lithium-sulfur battery using the reactive force field ReaxFF. A lithium-sulfur battery is a novel type of rechargeable battery known for its high energy density, several times that of the well-known lithium-ion battery. Without going into too much detail, the general working principle is as follows. The anode consists of lithium metal while the cathode consists of elemental sulfur. During discharge, the metal lithium at the anode dissolves in the electrolyte and the lithium ion moves to the sulfur cathode. There it reacts with sulfur to eventually form lithium sulfide. The storage of lithium ions inside the sulfur is accompanied by a large volumetric expansion of the cathode, which is actually one of the challenges faced in the design of these battery materials. During charging of the battery, this process is not just simply reversed. Instead, lithium polysulfides are formed and leaked from the cathode. These highly soluble polysulfides get dissolved in the electrolyte and shuttle the lithium ions back to the anode. This causes a variety of issues. Among them is the degradation of the anode. In the following simulation, the charging process is not considered, but for those of you wondering, it may be good to keep in mind that the charging process is more than just a rewind of the discharge process. With these basic principles of operation in mind, let's have a look at our modeling approach. Instead of creating an atomistic model of a complete battery, we will only model the chemistry on the sulfur cathode explicitly and consider the anode to be an implicit lithium reservoir. The battery is discharged when the lithium reservoir and the explicit sulfur cathode are in thermodynamic equilibrium. That requires that they are both in thermal and chemical equilibrium. In the language of statistical mechanics, the possible states that represent this thermodynamic equilibrium are called the Grand-Canonical ensemble. To generate this ensemble, a Grand-Canonical Monte Carlo procedure is used. Here's a quick sketch how it works. The Monte Carlo procedure generates random modifications of the sulfur structure. Monte Carlo moves that result in a structure with a lower energy will always be accepted, meaning that they will replace the current structure. Moves that result in a structure with a higher energy are only accepted with a certain probability. This probability becomes smaller the higher the energy difference is. The Monte Carlo moves all apply to the sulfur cathode, as the anode is taken to be an infinite and implicit reservoir. The following Monte Carlo moves are possible: random insertion of a lithium ion, removal of a previously inserted lithium ion, random displacement of a previously inserted lithium ion, or a shrink or expand of the volume. Throughout the whole simulation, the lithium reservoir will only be represented by its chemical potential, used in the calculation of the acceptance criteria. For those of you interested in technical details, a more detailed description of the Grand-Canonical Monte Carlo algorithm in AMS is available on our website. I've put an according link into the video description. Let's begin by importing a sulfur crystal structure into AMS input. This crystal structure is available for download also in the video description. Just open it. And then we change to the ReaxFF engine. And following the literature approach and the tutorial advice, we shall use the dedicated lithium-sulfur force field. And we wanted to optimize the geometry. If we click on the arrow button here to the right, we get to the settings, to the details panel for the geometry optimization, and there we tick the box Optimize Lattice and then save the calculation and run. I will call it Sulfur Opt for optimize, save, and then just file and run. Now you can see that in AMS jobs a window will open up showing you the details or some status information on the calculation. It has already finished, and we want to update the structure, and you can see it was already fairly good. There were only small changes. Now let's look up the total energy of the optimized structure. We just switch back to the AMS jobs window, and with the job still selected, we click on SCM output, which will open the text output file of the calculation. And then we just scroll down until we reach a section called Calculation Results, and the first entry in there is the total energy of our system, is given in atomic units in Hartree, so minus 13.610 and so on. That is 8,540 kcal per mole, just as described in the online tutorial. In the next step, we are going to calculate the chemical potential of lithium that we need for the Grand-Canonical Monte Carlo calculation. And following the literature approach, we take the chemical potential of lithium to be the energy of one lithium atom inside a structure of body-centered cubic lithium, BCC lithium. And for this we need to run another calculation. So we are opening a new input. And instead of importing the structure, we now are creating the structure with the input tools of AMS input. And we begin by going to the Edit menu, Crystal, Cubic, BCC, Body-Centered Cubic, BCC, click, and we are going to use the lithium preset. We click on OK, and we see one lithium atom. We can switch on the periodic view to repeat the unit cells. Switch that off again. Now we generate a supercell. So we go to Edit, Crystal, Generate Supercell, and again, following the tutorial, we shall go for a supercell with 8 by 8 by 8. Okay, so that's our bulk lithium structure. If I hit Ctrl A, I can see that it consists of 512 lithium atoms in one unit cell. Now let's hop back into the ReaxFF engine and select our force field again. This is the lithium sulfur force field that we want, the same as before. And then we basically repeat the calculation that we have carried out for the sulfur structure. So we request a geometry optimization, and we go to the geometry optimization details panel where we check the checkbox Optimize Lattice, yes. And now we can also save and run this calculation. I'm going to save it as lithium opt. And then just go to File, Run to run the calculation. And the geometry optimization has already converged. We want to update the structure in the input window again and look up the total energy. So we go back to AMS jobs, and with the last job selected, click on the SCM menu, Output, and scroll down into the calculation results. Again, the total energy is the first entry, minus 30.76 and so on and so forth. Hartree. This is minus 19,304 kcal per mole. And since we have 512 atoms, we divide that number by 512 to yield the energy of a single lithium atom inside this structure, and get a value of minus 37.7 kcal per mole, which is taken to be the chemical potential of our lithium for the coming Grand-Canonical Monte Carlo simulation. Okay, now let's set up the Grand-Canonical Monte Carlo calculation. Just reopen the window or the calculation with the sulfur structure that you have run earlier, and make sure that the structure displayed here is the optimized structure and not the initial one. Change the task to GCMC, which is the abbreviation for Grand-Canonical Monte Carlo, and click on the Details button right next to it. Then change the ensemble to be mu PT, constant chemical potential, constant pressure, constant temperature. As I mentioned earlier, the cell will shrink and expand. So if we select an ensemble with a constant volume, that will not be possible. Then we set the number of GCMC iterations to 1000, and then go to Add Molecules Within and Add Molecules Not Closer Than. We want to add molecules within a radius of 6 angstrom, but not closer than 1.2 angstrom. Again, these values are taken from the online tutorial. And finally, we click on the plus button next to the entry molecules all the way on top. And request a new molecule. This will open a panel in the molecule view window, an empty one. And in there we position a lithium atom, a single lithium atom. The position of that lithium atom inside this unit cell does not matter, but for cosmetic reasons I shall center it real quick. So I'm going to edit crystal, set 0.5, 0.5, 0.5, and this will center the atom in the center of the unit cell. Now we can rename this panel to lithium if we like. If we click on the arrow here, we get back to our initial panel that contains the sulfur structure. I shall name that Sulfur. Again, this is only for cosmetic reasons. And then we can enter the chemical potential of the lithium that we have calculated before to be minus 37.7 kcal per mole. Now, if we would like to pick another unit, we can always click on the units to open a drop-down menu from which you can select a different unit. We stay with kcal per mole for now. And now all that is left is to save and run the calculation. We go to File, Save, Save As, sorry. And then we name it GCMC. Save. And run. Now you can see that the calculation is started. And with the current running calculation selected, you can click on SCM Movie to follow the process of the calculation. This calculation will typically run for around 1 or 2 hours on a normal desktop computer. And we shall just use a fast forward here, and then I will show how to analyze the calculation once it has finished. As the simulation proceeds, you can clearly see the different Monte Carlo moves being carried out. Now that the simulation has finished, we can take a look at the results. Let's first have a look at the change of the volume. Go to Graph, Cell Volume, to display the volume of the unit cell during the simulation. The units are given in angstrom, in cube angstrom here on the right. To calculate the discharge voltage profiles as a function of the lithium intercalation content, we shall make use of a small Python script. The execution of Python scripts depends on the operating system you are on. I will put a link in the video description that explains how to execute Python scripts with AMPs for various platforms. I am on a Windows computer here, so all I have to do is go to the Help menu and click on the entry command line. Once the command line has opened up, I will type in the command bash and hit enter. This will bring me to a minimal Unix-like shell. This pre-configured amps command line will open in the correct directory. All you need to do is download the Python script and place it next to your results folder of your trajectory. Once you have done that, you can simply run the calculation by typing in the following command. $ampsbin plams, one space, then the name of the Python script, lithium voltage profile.py, -v results dir equals, and then the name of your results directory. In my case, the calculation was called GCMC with small letters in one word, so the results directory is called gcmc.results, and then we just hit enter. Once the calculation is finished, the results will be printed to the command line. If we just scroll up a bit, we can see that the first column is the number of lithium atoms, the second column is the fraction of lithium atoms, and the third column is the voltage in volt, while the fourth column is the volume in cube angstrom. We can plot these results with standard plotting software, and if we do, we will see that the voltage curve compares nicely to the experimental values. Don't be concerned if your results look a bit different. Monte Carlo calculations rely heavily on random numbers, and while the overall trend should be reproduced, single runs may differ from each other. That brings me to the end of this video. I hope you found this small demonstration useful. You can find many more videos from different areas on our YouTube channel, and if you're missing something, just let us know in the comments.